Let's do a couple of examples for ductile materials. This is example number one. In this example, what we have is several state of stresses, and for each one of these state of stresses, we want to find if given state of stresses, this is actually safe. And the material is a heat rolled steel, and the strength of this material is given, so we know what the strength is: 100 ksi in tensile and also 100 in compression. So we can assume that these values are same. That's what they're doing. And in the problem that you need this information is given by the E Young's modulus 40,000 ksi. And what you need to keep in mind, you need to watch out for these units very carefully, because many times what you get in the textbooks and from tables is 40 MSI, okay? But 40 MSI converts to 40,000 KSI. You want to keep all the units as same as possible, okay? So the other thing the problem tells you is that you have a true fracture toughness, a strain toughness of 0.55. That is actually bigger than 0.05. So you're already telling that we already know that we are in the plastic zone. And just because the fact that I have a plastic region, that tells me the material is ductile. If the material is ductile, that means that I need to use the theories related to that. Okay? So before we start the problem itself, let's just fix a couple of ideas here. In this particular problem, I don't have a design factor. Okay, it doesn't tell me to use one. So we will assume that's equal to 1. But you should know that typically when you solve the problems and something is not given, you may want to ask out with the program that you're working for, but use a 1.15 as a base. So that means that, let's say for the very first case that I'm working with, right? This is your very first case. So this case, you have the stresses. So what we are saying is that what you will use for sigma xx would be 70 times 1.15. You will use 70 times 1.15, okay? And then tau xyz is 0. But we will not do this in this problem, okay? So we are not going to assume this. We're going to assume a safety design factor of 1. And to solve these problems, we have to keep in mind a couple of things. We have 3 theories. The first theory is we need sigma equivalent. Okay, the sigma equivalent is the distortion energy theory, and for that I need the value of sigma equivalent. I need to use the maximum shear stress theory, and for that we need tau maximum. And ductile column Moore theory basically uses sigma 1 divided by sigma in tensile, S in tensile, sigma 3 divided by sigma in compression. Okay, so we have those values. The very first thing that we do in this problem is we're going to convert this and write this, the state of stress for this. The state of stress is 70, 0, 0, 0, 70, 0, 0, 0, 0. So this is, from here, we need to find what sigma 1 is, sigma 2, sigma 3, and tau maximum. We need to find those values. And note that this was 0 and everything else is 0. So this is a couple of things we can say. This is a state of plane stress. We can also say this is a state of principal stress. Why? I only have diagonal terms. So without actually running any code or anything, you can immediately know sigma 1 is 70, sigma 2 is 70, sigma 3 is 0. So you know your principal stresses, okay? And if you want your tau max is nothing else than sigma 1 minus sigma 3 divided by 2. So that would be 35 KSI. So we know what your principal stresses are. Now, what we want to do is we want to find what is your factor safety, right? So to find the factor safety for each one of the cases, for each one of these three cases, we are going to use our MATLAB code to assist us. So we know, so let me just pull the MATLAB code here. Okay, so this MATLAB code, this is what it does. So what you want to do is you want to go to folder where you save it. And this file that says main, that's the main file you're going to run. To run it, you press here. And the brittle theory is all the theories related to brittle materials. This is ductile materials. This is a preliminary information. This is to plot the arrows in your diagrams, failure diagrams. These are the function calculates the principal stresses. This calculates actual component stresses, and these are your units. So this is the main file you're going to run. So let's run this file and see what happens. So I'm going to run it. Once you run it, you can ask a couple of questions. The first question is in inches. Yes, we are working in inches. We are working in KSI. And like I told you, we are going to assume this is equal to 1. Please make sure that when you're running this code, even if it's 1.15, you need to enter 1.15. You cannot leave it in blank, otherwise it will give you an error. So what do we know? Well, in this case, I don't know loads, I know stresses. So I press number 2. And I'm working with ductile materials. I press number 1. Enter yield strength, compressive strength, and your modular elasticity. And now it says, give me the stresses. Now, note, just pay attention to a couple of things here. In this particular problem, let me change the colors here. In this particular problem, you should know that your sigma xx is equal to sigma xx axial plus sigma xx bending. All of this is equal to 70. So in the code, I need to put one or the other. I could say this is 70 plus 0, but I cannot put 70 and then put another 70, otherwise it will become 140. Okay, just keep that in mind as you're doing these problems. So that's what I'm going to do. Just for the sake of this example, I'm going to put, 70. Okay, put the 0 here. And then this is 70, and everything else is 0. And he says, do you have a design load factor applied in our problem? Yes, yes it is. Okay, so when you press that, you're going to start getting all the answers, and Nicole is going to run one more time because you're evaluating at point C and point A. You're going to evaluate twice. So you do have to enter these values again. So you say 70, 0, 70, 0, 0. Remember, the code is done for a generic case. That's why it runs twice. So you can evaluate point A and point C. And I'm going to go over that especially in the next example to explain why it does that. Okay. So it's completely done, and your answers are going to be, so when you complete your code, first of all, you can open one of these plots. Okay. This plot basically gives you what your Moore circle looks like. And he says this is at the point A, so working it, assuming that you're at the point A. So this is your design point right here. And what we can see in this problem, I am inside this all safe region. So therefore, I will be safe for all three theories, because inside this region is a safe zone, that nothing has failed in this region, okay? So, but if I want to do this by hand and I want to do the calculations, I have a file called Ductile, okay? In this file, you're going to have all the checks that you need to do. The very first check you do is the tensile and compressive checks. Okay, so and you can basically use your code for this, and I don't have a problem with that. But you just have to actually write it down. So I am expecting you will say, okay, this is sigma yield over S1 or sigma 1, right? So that would be 100 over 70 will give me 1.29. And then your compressive would be sigma compressive sigma 3, and that gives you minus 100 divided by 0, gives you infinite. Means that this has an infinite margin of safety, means that there's actually never going to fail in this region. Okay, so the second one is we want to use the distortion energy theory. Okay, the distortion energy theory, I need to find the von Mises, and the von Mises is sigma equivalent. There are many ways to find this. One way to find it is using this equation. Sigma 1, sigma 2 minus sigma 2, sigma 3 minus sigma 1, sigma 3. Okay, so this is the most general case, and if we evaluate all the values in here, in our problem, your state of stress, remember your principal, your principal stresses were sigma 1 is equal to 70, sigma 2 is equal to 70, and sigma 3 is equal to 0. So if you plug in all the values in here, and you can see that your MATLAB code actually does it for you. You see, it evaluates everything for you and tells you this is equal to nothing else than 70. So what you get here is this is equal to 70. If I evaluate all these numbers, I put all the numbers in here, where this is 70 squared plus 70 squared plus 0 squared minus 70 times 70 minus 70 times 0 minus 70 times 0. Evaluate all this, I would get a value of 70 KSI. Okay, so this is your distortion energy. So now I can go ahead, I can take this value and I can find my factor of safety. My factor of safety will be sigma yield in tensile divided by sigma equivalent, and that would give you 100 over 70, which gives you 1.43. Okay. The second theory is the maximum shear stress theory. And the maximum shear stress theory, there are two ways you can do this problem. In the strict sense, the maximum shear stress theory is you need to find this, and this is sigma yield in tensile divided by 2. There's another approach that we can use. It's not the strict sense maximum shear stress theory, but this we use it very often in the industry, and actually we will use that in the next couple of chapters. And it's also very well acceptable and comes from your distortion energy theory, actually. Is divided by 3. So let's do it both ways to kind of see how that actually works out. So if I did this, this is actually equal to, you can see 100 divided by 2 is equal to 50, right? And from here, your factor of safety will be your maximum yield shear and tau maximum. Okay, so that would give you 50 divided by 35 and gives you 1.43. And the same, and then on this side, if I did this, you find that this is equal to 57.735. So what you find in this side here is your factor of safety will give you 1.65 now. But when I talk about maximum shear stress, I'm really talking about this one. Okay. And the code actually, when you're running the code, it gives you all these values. You see, it tells you this. But when you're doing this by hand, I'm expecting that each one of us will go ahead and will write down these equations by hand. Okay. The ductile column Moore theory, what he says is that your factor of safety is nothing else than 1 divided by the absolute value of sigma 1 divided by sigma yield in tensile minus sigma 3 divided by sigma yield in tensile in compression. Okay, and if you replace all the values, you find this is equal to 1.43 as well. So in this particular problem that we are solving, what you can see is the code gives you all that and makes you run it twice actually. And then it gives you your principal. So when you put everything, gives you what your principal stresses are, and goes and calculates the average of this for the maximum shear stress theory or von Mises. But you use the average for those two theories. And then you just go ahead and does all the checks for you that you need to have for this particular cases, and at the end of the day it gives you a nice summary of at point A, and you know, say the design is at point A, it doesn't really matter point A or point C, because both are actually giving the same value. We don't know where this is located. Okay, so this kind of tells you what is really it tells you what the values are, and so this is the theory that we typically use, and it's very popular, and the one that we all, you know, we want to use in this course. So we are going to solve now the second problem. In the second case that we want to solve, though it's kind of the same thing, in this problem is very interesting because in this case, everything is zero except one shear, right? So this is shear based more than anything else. Okay, so this is a case what we call pure shear. We don't have nothing else in the problem. So I want to solve this whole problem, but let's go ahead and do it using our MATLAB code. Okay, again, you use failure theory and you run the MATLAB code. When you're running it, give me a minute. Then this is 1 inches down here. I'm writing here. This is inches. We're working KSI. We're going to use 1 as a factor safety. I have stresses. I'm working in ductile materials. And this is 100, 100. This is 40,000. Axial, this is 0 in this case, right? This is all 0. And tau xy, now the same thing. I have to add in one place or the other. I can add both. So I'm going to add 45 here, put torsion 0, but it's all the same probably the other way around. Okay. And yes, the design factor is applied. And when you run the code, so this error I am getting is because I had the plot open. Okay, so you need to make sure that all your plots are closed before you run the code. Run this to fix few things so we can run it again. Stresses, ductile, 100, 100. This is 40,000. In this case, there's no axial load. We only have, I'm going to use the same assumption as before, right? This value was 45. I'm going to add it to only one spot. 45, put a 0 there. 0, 0, 0. Yes. and you can see that the code ran completely. And what's very interesting here is, and I want to point this out, that the maximum shear stress theory, if I use this theory, and the distortion energy will give you exactly the same value for the case for pure shear. Okay, and let's go ahead and see what the plot looks like. And you can see that this is your plot, and you are actually inside this region. Okay, and since you're inside the safe region, you can say your design is completely safe. And remember, when you're done evaluating this and looking at the plot, you need to always close it. Okay, just and I also want to point out, so you have, this is the distortion energy theory out here. This is the they just give you the same value, the more color ductile color more and the maximum shear stress theory for this particular example. Make sure you always close it before we move on to the next problem. Okay. The next question that is asked is, what happens with this case? This particular case, your stator stress is equal to minus 40, 15, because symmetric, minus 60, 0, 0, 0, 0, 0. Note that in this particular case, this is a plane, state of plane stress, because I have one plane that it has all zero stresses. So this is actually confined to the XY plane. Okay, that was the case. Let's go and run this problem again. Go and choose your failure theory and you press play or run. This is inches. Working. This is 1. Again, as we talked about, we will assume that your design factor here is 1. Working in pure stresses, working with ductile materials, this is 100, 100. Your E is 40,000. And then the axial load, again, the same logic, right? If I put minus 40 there, put a 0 there, because it's the addition of those two values. In this particular problem, this is minus 60. This is 0. This is 45, put 0 there, and everything else is identically 0. Okay? The design, so yes, the design factor is applied to the loads. You run the problem. So you're just going to run it. And these are your safety factors for this problem. Let's go ahead and see what your plot looks like. And you can see that you are basically, your plot is right here, and it's saying it is completely safe. And you can see that what I am getting here is they're all basically equal to 1. So when you're saying this is all equal to 1, what you're saying is you're basically saying that you almost have you have your capability, basically the onset of failure, but you're not there yet. You still have a little bit of cushion to go there. Okay. Then let's go ahead and run the very last case. Okay. So I have this case now. I just wanted to point out that here in the file, ductile, again, you have everything that you entered in the problem way multiplied, and then tells you what your, this is your state of stress, tells you what your principal stresses are in the problem. And then, as you can see in this particular problem, they're all negative. And then it gives you all the checks that you're looking for, your compressive checks, your tensile compressive checks, uh, tells you what your von Mises stress is, your distortion energy theory, goes and calculates your tau maximum. That's actually equal to 48. 48, you divide your sigma yield in shear by 48, then you get 1.04. And then you can do the same thing if you divide it by 3 and you get 1.2. So basically, that's how you solve this. So your code gives you all the information. So let's go ahead and run your next case scenario. Okay, in this next case scenario, you're going to run it. Your selection again is inches. You're working in KSI. This is 1. Stresses are we have stresses. It's ductile material. 100. This is 40,000. And now all my axial, all my normal stresses are 30 KSI for this particular example, and everything else is 0. And you wait for this to run. And then once it runs this, let's open this. And you can see that your point in this particular problem, your point is right here. Something. And it is completely correct here. This is sigma 1, this is sigma 3. And what he's saying is that if you are failing in this direction, this is a pure shear failure. This is pure tension failure. So you can tell from the problem itself, hey, I got everything in tension, 30, 30, 30 in the diagonal term. It's a point in your Mohr circle. So therefore, and it's a point in the tension direction. And you can see that the fact that you get all your margins of safety equal to 0, what that is saying is that everything here is actually completely safe. So this completes example number 1.